And say I give you, you guys, as we do this, give yourself some space because I'm going to add a problem to the bottom of this page, okay? All right, so here's a very basic parametric equation, and I want to find the arc length from in between 1 and 4. Everybody good? Okay. And so what I need to find first is dx dt and dy dt. What's dx dt? 12t. dy dt? 6t squared. So if I want to find the arc length, I integrate from 1 to 4 on the square root of 12t squared plus 6t squared dt. And from here, throw it in your calculator.
Does it matter if we're still in parametric?
In fact, you will see that if you're in parametric mode, when you go to type in the integral in your calculator, it's going to give you t.
Does that matter? That's fine.
Yeah. And, well, I mean, we wrote this in terms of t, so.
Yeah, but if it was still in...
No, it won't make a difference. If it was, like, if you had it back in function form, it would give you the same answer.
10,389. I don't know if I put it.
I got 156.52. The square root. That would do it. I wonder if you took this, would that... No. What did you say you got originally?
It's like
10,000?
10,000.
Are we good? Not bad, right?
Is there units on?
Technically, it would be units. Unless you had, like... Okay. So the next thing I want you guys to think about is... I'm going to create a different problem here. And this is why we do parametrics. Okay? 100% this is something to help us understand why parametrics are powerful. Okay? So imagine I have a circle with radius 4. And then on that circle, there's another circle with radius 1. All right. And you guys see how I have this like highlighted point here? Okay, of where they intersect. But what's going to happen is we're going to take this little circle and we're going to rotate it around the big circle. Are we good? So I might get a new circle here. But what's going to happen to this point? It might be right here. And then once it gets to here, and these are, so think of each one of these as this could be like t equals 0. This should be t equals 1 because it's happening over time. Okay? And that special point might be right here. And then we get to here. And then it's back around to here. You guys get the basic premise of this. Okay? And so if I were to trace the point of that red point, it would trace to here. Everybody good? And then if we kept going, it's essentially going to keep doing the same thing each time around the circle. And we call this graph an epicycloid. I had to double check the spelling. epicycloid. Now, if I asked you to create this in your calculator, it would be a very challenging thing to do unless we use parametric equations. Everybody good? Okay. So, the equation, the parametric equation for this graph is x equals 5 cosine t minus cosine of 5t. And y is going to equal 5 sine t minus sine of 5t. Everybody good? All right. So if I want to find the arc length of the epicycloid, we have a slight problem. Does anybody want to guess what that problem is? If I'm describing this, you see that sharp edge there? It's a cusp. Is everybody with me? Okay. So to find the arc length of the whole thing, we're going to find just this arc length and then multiply it by 4. All right, so now we got to figure out, well, what are the angles for t that get us from here to P? Well, are you guys with me that this is currently the point 4, 0? And this is the point 0, 4. Okay, so for the first one, we're going to do 4 equals cosine of 0 minus cosine of 5, 0. Wait. Oh, that's where t equals 0. Yeah? So that one's easy. What about up here? What value of t would give us here? Pi over 2. And then, so then we would have our square root. What am I filling in for dx dt?
Negative 5 sine t minus, or sorry, plus 5 cosine, or sine t.
5 sine 5t. Yeah, okay. Plus. Thank you. You guys, what's dy dt? Don't forget your dt. Then you guys, again, if it's using the integral, I care more about setting up the integral than I do about solving the integral. Okay, so this is a place where you can just plug this in your calculator. What are we getting? We should get 10. How we feeling, okay? Yeah.
If you wanted like to get this smaller circle to like rotate around it like more than like 4 times.
I don't think you can. Like, I think this was set up in such a way that, because there's still like perimeters matching up. Or circumferences matching up, I think. I got to think through it some more, but I think that's where the issue becomes. Like, let's see, the circumference of the big circle would be 8 pi, right? And the circumference of the little circle would be 2 pi. Hence, it goes around it exactly 4 times. Does that make sense? Think about a tire on the road. Unless the tire's slipping, it rotates the same rotation. Like, you can't, making the tire go faster doesn't change the distance. It changes the. Does that make sense?
Yeah, no, I just remember like I saw something like there's like a problem like this that I saw like somewhere, and it was like kind of like, but it was more like how many times does it go around the circle?
Yeah.
But it was like, yeah, like the wrong answer was like they put it was like on like the SAT or something, and it just sounded like, but like the SAT like got it wrong. Like they said it would be 4 times, but it was like actually like 5 times or something, because like because you have to go from like where like the center of that circle, the outer circle is, because like the outermost part of the circle doesn't rotate. Like,
well, so it tells you what the so you'll notice that this equation is based off of 5, yeah?
Yeah.
Okay. That's because this distance is 5.
Yeah.
Instead of basing it off of this distance. Like, I could see that being a thing, but that would be in terms of where did these 5s come from.
Yeah.
And so, like, yeah. Everybody good? All right. So originally my plan was to do these notes yesterday and then give you guys time to practice these problems today. So I'm going to let you guys practice these problems today, if that makes sense. And then tomorrow it's do whatever you need to do. You have a quiz on Friday. Did you guys catch my drift? And I will be here to do whatever you guys want to do.